Hey gang, we are looking at these practice exam questions. We looked at question 1 and 2 in class. Here is question 3. A particle undergoes linear acceleration according to this equation. Now, given that the particle commences motion at the origin with a velocity of 4 meters per second, what is the particle's displacement to 4 decimal places when v is 10, given that x is less than 0? Now there's quite a bit of information there given, so whenever we work on these problems we need to start with a derivative that relates acceleration to either velocity or something else. So looking at the forms of derivatives for acceleration, we have a is equal to v times v dv dx. Okay, now this part is useful here because the rest of the problem speaks only about displacement, which is your x, and mentions velocity, okay, which is your v. So there's no t variable there, and that means we don't need a derivative with a t variable in it. So then we know what a is. Since we know what a is, we're going to use that and put it into the left hand side of the expression and set it up like this. Okay, now from there we're going to do a little bit of rearranging, treating our derivative operator similar to a fraction, and separate the parts, all the x parts on the left hand side, or the right part, or the v parts on the right. Then we integrate. Now, integrating with these endpoints is a convenient way of solving the problem in one go without needing to introduce a c parameter, an integration constant, and then substituting to solve for the integration constant. So the way we do it is the lower limit here, those ones there, well, that's where we put our initial conditions in. Okay, and we put the initial condition for x and for the corresponding v value. So we know initially the value for displacement is 0 because it is a motion commencing from the origin. Okay, that means x is 0 at the origin. And then we want to know what is the particles, and this occurs at the origin. We've got 4 meters per second as a velocity, that's this bit here. And then in the future we want to know what the displacement is when v is 10. So we set up this integration equation like so, and we don't need to work that out by hand, being a multiple choice question. We go ahead, plug it into the CAS like this using the solve command, and then when we solve we get 2 results, and we have to recall that given that x is less than 0, the result must be the -1. So the answer is A. Okay, next question, question 4. A tram accelerates from a tram stop at a constant rate of 8 meters per second squared from rest. It then begins to decelerate at a rate of 3 lots of 8 meters per second squared until it comes to a halt at the next tram stop. So that means it's going to stop and have v equals 0 at some point. If it travels a total distance of 350 meters over 90 seconds, what is the value of a for acceleration? Well, there you go. Now the best thing I would do here is try and depict it as a velocity versus time graph. So draw a diagram. There we go. Now this diagram has the tram accelerating at some constant acceleration, constant rate, and then rapidly decelerating at 3 times that rate. It has a total time of journey of 90 seconds. Okay, and what we have here, the total distance, well, that's the area under the curve. So 350 meters is this area under the graph. Okay, making sure we label our parts. When we think about acceleration, we're talking about the rise over run of this line being gives you a units, and this one is negative 3a units. And one thing we notice is the shape we've produced is a triangle. So being a triangle, we have a height. Now the height of the triangle is aligned with some point in time t0 and another height of v0, corresponding v0. So that's going to become important very soon. So the first thing, once that's established, the first thing we have to understand is that we've got a triangle, and the area of a triangle is the same as the area under the curve. Okay, so we can use area of a triangle rule, half base times height. Area is 350. The base length is 90 seconds. Okay, and the height of the triangle is your v0. It's this one here. Okay, so using that we can rearrange and solve for the velocity. Maximum velocity achieved 70/9. Okay, so we now know the rise going up to the top of the graph is this v value. So we're going to use that and include it into a rise over run. So we have, for the first gradient here, a is a rise of 70/9 going up divided by the run. So the run is this time of t0 seconds, rise over run here for the first acceleration. And the second one, rise over run, gives you, we've achieved 70/9 over this amount of distance here, 90 minus t. And that gives you, in magnitude only, a gradient of 3a, and you'll see why in a second, why we need to have just the size of the gradient only. And it gives us these two. Now we're going to go ahead and solve both equations for t. Now when we're solving that, we're going to be doing it on the CAS, and we don't have linear equations, so we do it by solving a system of equations only, not linear equations. Okay, and we set it up in solve a problem like this, and we're going to solve for a and t, but really only the a value is what we're after. Okay, and we'll get our two results, and looking at the a value there, we can see, well, that must be answer B. Okay, very good. So we've finalized these two questions now, and please stay tuned for the next video, part 2, looking at a few more multiple choice and some short answers. Okay, well done everyone. 2. Alright, let's move straight into it. Question 8. The motion of a particle is given by this acceleration time graph below, where time t is in seconds and the acceleration of the particle is in a meters per second. Okay, so here's a motion graph. Now normally we're used to working with a velocity time graph. This is an acceleration time graph. Now from that, it says in the question, if the initial velocity of the particle is 24 meters per second, the distance traveled by the particle in the first 6 seconds is equal to. So we have to work out distance from starting with an acceleration time graph. Now that doesn't seem to be straightforward, because normally we could get distance or displacement from a velocity time graph, being the area under the curve. Okay, so if you look at an acceleration time graph, the area under this curve would give you velocity, not distance or displacement. So can't really approach it by examining area under this straight line curve here. It's not going to get us close to distance. So we got to think about it another way. First off, reading from the graph, we notice, okay, straight line. So if I work out the equation of this straight line, I have a function for acceleration in terms of time. So let's aim for that. Rise over run gives you -6. You can examine that by seeing how many units in rise divide how many units in run, and then we're going to use this formula. This is the formula for working out the equation of a straight line. Substitute m equals -6 and taking a point such as, this point here. When x is 4, you have y equals 0. Okay, so where do we get up to? We're finding the equation of the straight line to know some relationship between acceleration and time. And so in terms of a and t, acceleration, we've got acceleration equals -6t plus 2. Now, from that, we have to work out what is going to be the position, or and then we can get the distance traveled. Okay, so we have to use calculus. We have to integrate twice. First, we can integrate to get the velocity. Okay, and so we get a quadratic from a linear function. Now we're told in the information coming down here at the bottom part of the graph in the question, if the initial velocity of the particle is 24 meters per second, that means when t is equal to 0, we have v equals 24, and we use that to work out what is c, and we get c is 0. So put that together, we get our velocity function. Now when we integrate again, we're going to get the position, the displacement, but the distance traveled is going to be the displacement from the origin, okay, from 0, and up to t equals 6. So the distance traveled in the first 6 seconds, you can work that out by doing a definite integral with limits from 0 to 6 and integrate velocity to get your distance traveled there. Here we go, part 3 of our practice SAC questions. Something to entertain you on the Sunday morning. Here we go. Alright, so we have this question. The velocity time graph below shows the velocity of a lift as it travels from rest to the 12th floor of a tall building during 2 seconds of its motion. Very good, pretty graph. The velocity at time t seconds from 0 to 2, okay, is given by this function, okay, v equals t squared times 3 minus t. Now, I've underlined that because really that is the most important thing to consider. The rest of it, after the first 2 seconds, the lift moves with a constant velocity 4 meters per second for a time and then decelerates to rest in the final 2 seconds. Acceleration of the lift is a. The velocity time graph is symmetrical about t equals a half t. There's a lot of information there, and we got to ask ourselves, is it really that important? And let's look at the question. Part A. Express a in terms of t for the first 2 seconds of the motion of the lift. Alright, so we really are just focusing on this part of the graph only. That's what part A is only pertaining to, only for the first 2 seconds. So all the rest of information describing the graph and the graph itself, really it's kind of a bit of a redirection and trying to confuse you a little bit. That's nasty. Alright, let's keep going. So first off, we have the acceleration. So to find the acceleration, we take the velocity function and we differentiate with respect to t. And we can do that using the chain rule. So that's u times v dash plus v times u dash. And we get this function in its simple form. Okay. and it's quite straightforward function. It's a quadratic. I'll just put the thing on the t there, and we're pretty much done for that question. We just state it nicely at the end and we will get our mark. Okay? Now, I just wanted to bring your attention here to the graph. That point there is an interesting feature of the graph. It's called a point of inflection, and it is a point where the gradient of that slope is the most steepest. So let's just highlight that and consider that for a moment. Let's look at the next question. So, hence, find the maximum acceleration of the lift during the first 2 seconds of its motion. So when we see that term hence, pardon-moi, when we see that term hence, that means use some result you got from the previous question and to help you answer this one. Now, thinking about the maximum acceleration is kind of like that. It's that point of inflection on that graph. It's the point where the gradient, the steepness of the graph, be it acceleration in this case, it's the point where that is the largest, the maximum. So this is what we're looking for. And the idea to find points of inflection is the second derivative. So we take our velocity graph and we have to differentiate twice to find the second derivative when that is equal to 0. And this will give us our point of inflection. Okay, so we differentiate the acceleration function that we used from the first part, and we're drawing on the answer from the last question to help us answer this question. We're going to differentiate it one more time. We get a nice linear thing. So then the maximum acceleration occurs when this derivative is equal to 0. And we get t is equal to 1 second. So that's right in the middle, symmetrical. This is the whole idea of the graph being symmetrical. So it brings your attention to the fact that, okay, if it's symmetrical, then I can find a point of inflection where we have either side of that point of inflection is the same kind of graph. It must be some cubic expression, this point of inflection. Alright, so having found that, we're going to take this time, t equals 1, we're going to substitute it into our acceleration function, and we're going to evaluate. And we get the value for the maximum acceleration, 3 meters per second. Okay, very good. Okay, so we have a mass has acceleration a meters per second squared given by a equals 4 minus v squared, where v is in meters per second squared and is the velocity of the mass when it has a displacement of x meters from the origin. Find v in terms of x given that v is equal to minus 4 when x is equal to 2. Okay, so we're trying to come up with a function of velocity in terms of displacement. So first off, what do we know about acceleration? Well, the acceleration has a number of forms, dv, dt, but the best one that we would need is the operator where it involves velocity and displacement. Okay, so that is equal to 4 minus v squared. All right, bring our terms together. So we have the velocity terms all here on the left hand side and dx on the right hand side. Now from that we're going to integrate. Alright, so the integral of that, we're going to have to use a substitution method. Okay, so from that we have the u dv, the negative 2v, and from that by transposing this little equation involving the derivatives, we've got half of the du is the v dv on the right hand side. So that's important because here we have, as you can see, there is the v with the dv, okay, and we're going to replace the v and the dv together with this negative a half. So that stuff goes out, and in its place we're going to substitute a u and our negative half du. So the integral now becomes, we've got this negative a half, so it's a 1 on a u du integral, okay, and here on the right hand side we're integrating, as you can see, the integral of the number 1 with respect to x, and that just becomes x and our constant plus c, so we can add that in now. Now back here on the left, well, that goes to a natural log of u equals, now some things we can do is deal with our negative a half. We're going to take this negative a half and move it over here to our right hand side, to our x terms. So multiply by negative 2, negative 2x, and we've still just got our constant plus c. So we don't need to do anything to the c when we're multiplying or dividing or adding to c. It's still just some constant number. Alright, so from that we have, let's substitute u in again. So that's our original substitution we did, so let's bring that back in, and we've got a natural log of 4 minus v squared is equal to the negative 2x plus c. Alright, now let's transpose for v. Our job is to get v in terms of x. So exponential on both sides. Okay, so we've got the e to the power of negative 2x, and the plus c, well, remember, using an exponential law, the e to the power of c comes out the front, and we're going to call it some other constant a. And let's just note that down to say that we did that substitution. There we go. Okay, so this is a good point to draw on our initial conditions. So initial conditions here, okay, when v is negative 4, our x is equal to positive 2. So we've got 4 minus negative 4 squared, and that's going to give us an a times e to the negative 4. All right. So what does that become? Well, left hand side here goes to 4 take 16, which is a negative 12. And this is a to the power of, well, a divided by e to the power of 4, because it's got that negative power. And so therefore a is equal to this result. We have negative 12 e to the power of 4 as our result for our constant a. Okay, so now we've got to include that back with our original function. Let's do that up here. Okay, so therefore we're going to get, we've got this 4 minus v squared is equal to, now a is, we're going to take that, use this calculation for a, right, negative 12 e to the power of, and now the whole lot in the exponent will be a minus 2x, the whole lot in the exponent, that's this part, looking at this part here,
and now we have to do plus 4. Okay, so now let's just transpose for v. Alright, so we get v squared is going to equal to now 4 plus a 12 e to the minus 2x plus 4. Here we go, and finally, therefore, v is equal to the square root of 4 plus 12 e to the minus 2x plus 4. But we just did the plus and we just did the square root, so we have to remember to include the plus and minus. Now, this point here, we haven't finished. That will give us 3 marks. Now, to get our 4th mark, we have to decide if it's going to be the positive square root or the negative square root. And we have to come back to our initial condition. So, since v is equal to minus 4 when x is equal to 2, so if we use that initial condition again and we substitute it in, okay, we would realize that we'll have a square root of a 4 plus 12, which is square root of 16. It's going to give you a 4, and we must have the negative to make sure it's the correct version. So it's the negative square root that's important for our rule to meet the initial condition. And I think we're done. There we go, and that's our 4th mark, and we're finished.
Next bit. Now, we did have another question, question 3 on the task. Now, I'm going to leave that question for a little bit and we'll come back to it another time. I'll put a separate video just for that one because it's a big question. But the question itself was slightly erroneous, and it would be an interesting activity to identify what's the problem with it. Okay, but first off, let's focus on this one, which is question 4. So we've got the velocity of a particle moving in a straight line is given by this velocity vector, velocity function with respect to t. Find the time when the particle comes to a stop momentarily. So it implies that it doesn't stop for a long time, it stops for just a split second in time. So we're looking at some continuous movement, some continuous graph. Okay, so when the particle comes to a stop, we've got a velocity of 0. So there's our starting point. We're going to let v equal 0. We let the function is equal to 0, and then we're going to solve for t. And we find that only occurs when the numerator is equal to 0, not the denominator, because if the denominator is equal to 0, we're in trouble. When the numerator is equal to 0, we get t equals a half second. Okay, straightforward, that one. Now, I want to bring your attention to a little bit more about this graph, this function and its graph. So, the job is to find the exact total distance of this particle at t equals 1 second. Now, first off, let's try and explore what this graph looks like. If you do this on the CAS and do it as a graph from 0 to 1, it'll look, and zoom in, it'll look a little bit like that. That's what you'll get on the CAS. And as you can see, we've got 2 parts there. We've got a positive area part, and we've got a negative area part. Okay, and the area under the graph is your distance traveled. Okay, so how do we handle negative area? Okay, that's what we have to ask ourselves. It is found by doing the subtraction. Okay, the subtracting the area that is negative in order to get the total area enclosed by the graph, which in this case it's the total distance traveled. Okay, now for us to work with this function, it's not really pretty. It's not in a good form we're used to. So we're going to rearrange it a little bit. And first off, we will see, I'm going to expand that 5 into the bracket. And then I'm going to add terms. I'm going to minus 5 and then I'm going to add 5. Now, the reason why I've done this is to manipulate my function a little bit. And you'll see what it does. I'm going to collect the minus 5 with that minus 10t. And what's left is just the plus 10 from the two positive 5s. And now I factorize this negative 5 out, and I've left it with a bracket factor that's the same as the denominator. Now it's very good because I've got a common factor that I can cancel. And I get that. And this here is a hyperbola function, rectangular hyperbola. Looks a little bit like that. And you can see the positive region of the little Cartesian plane. Looks very similar to the black graph there. Okay, so that's the same graph. It's correct function, but it's in a form now that helps me to integrate. And that's precisely what we're doing next. To find the total distance, it's the integral, okay, of our velocity gives distance. So we need to carry out an integral in such a way that first finds the area of the positive region of the graph from 0 to a half. That's the first integral there. And then the second integral is subtracting the integral from half to 1 of the same function. Okay, so that integral expression there will give you your total distance. Okay, now at this point in time, it's a CAS active task, so you can use your CAS to evaluate that, but what you do need to do is just do a couple of lines of working out to show that you can carry out the integral. Alright, this is your method. So first off, taking out that factor allows you to show I've got the fraction in a form where you have the derivative in the numerator of derivative of the function that's in the denominator. Now when you've got derivative of function divide function, that is a special form, and the integral of that is a log. Okay, so you integrate using CAS, and then we can go ahead and evaluate this on this thing here on the CAS, and we will get that as your result, 5 times log of 4 on 3 meters. Okay, that does not need to be evaluated by hand. It's a CAS active task, and that could be done under CAS. Excellent.